Welcome to today's webinar. The topic today is form finding and calculation of tensile membrane structures in RFEM6. My name is Andreas Hörold. I'm responsible for marketing and PR in the Luba software company. For instance, the website, the German and English webinars, customer projects, newsletters, and so on. I will be the moderator today, and I will answer your questions together with Andreas Niemeyer, but yeah, my two colleagues can introduce themselves.
Thank you, Andreas. My name is Stefan Hoffmann, and I am working for Luba for 3.5 years. I am mainly working in the support team, so I'm answering emails and phone calls, but I'm also involved in the product development for add-ons like form finding and cutting patterns, or as well for our standalone wind tunnel simulation, RWind. And so I'm gonna present you the webinar today.
Hello, I'm Andreas Niemeyer. I'm responsible for the product engineering here by Blueball. I'm taking care about all wishes, features. We think about how we can implement it, in which way, what should be behind, and create this with our programming stuff and testing stuff.
Okay, thank you for your introduction. Then we can switch off the webcams that the attendees can see the full screen. Before I hand over the screen to Stefan, I would like to describe how you can ask questions, at least for the attendees who participate the first time. You can show or hide that panel here that you can see on the right side of your screen. Show it with that arrow, and then you can enter a question here. And yeah, we will answer you. The other way is to watch the entire webinar, and then you can email your questions to info@blueball.com. Okay, that's all for now from my side. I hand over the screen to Stefan. Stefan, it's your turn.
Yes, thank you. So I am currently sharing only my normal monitor. I will open the presentation, and if something is not working, feel free to interrupt me, Andreas. Thank you. So this is my presentation slide. As you can see, the content page, of course. So I have structured my webinar into 3 topics mainly. So in the first part, as usually often, I want to get you to know our new features. So which is introduced and what is gonna be introduced maybe soon. Then in the next part, we are going to check some different membrane and cable constructions. So it's not mainly for the design in this webinar, it's just about how to get used to our add-on, because I think that maybe there is not such a big knowledge as it is already existing for RFEM5, but you will find most likely the most functions and even more functions also in RFEM6 in our add-on form finding. Last but not least, I will finish then my presentation with a prospect of what is planned, and then I will hand back to Andreas. So let's start. I have some slides at the beginning where I would show you some key points of features. Then I will show you the feature directly in the program at an example. So the first feature I want you to introduce is the ponding load. This is not mainly limited to our form finding add-on. It's a normal load type, so it can as well be used in a, let's call it normal static calculation. But since its effect on, let's call it weak membrane structures, that you can have some water being accumulated at a certain area due to the weaker stiffness of our membranes, I want to mention it as well in our form finding webinar. The feature ID is shown on the top right. So if you are used to our extranet and you know where you can find new features or also bugs which got fixed, you can just look up for the feature ID and also get a brief explanation of the feature. So what is the ponding load capable to do? It is able to simulate the effects of rain or even snow. It depends on the specific weight you enter on multi-curved surfaces. So usually you, of course, want to avoid that rain will have a big influence of your membrane, but it depends on the shape and the pre-stress you can introduce into the structure if you will have effects, maybe also together with a wind load or a normal dead load. It considers the geometry and the displacement according to a third order calculation. Of course, using membranes and cables, it's most likely necessary to calculate it theory third order, because usually it's a nonlinear system which needs to be inspected with big deformation analysis. The last part is the analysis of approximately horizontal membrane roofs. So as I already told you, the more horizontal a membrane will be, so the higher the effect, depending on the pre-stress amount you put inside the geometry, may affect our results. Due to the fact that we, of course, also want you to be able to evaluate the results you receive by the load, you will see soon in the program, once I show you the example, that you will get two new entries, so the water depth and the water level, inside the shape surface result tab. I think usually if you already used our add-on, you should be, or you should know that the shape contour lines are a good tool to evaluate how the membrane will be deformed. And last but not least, we also introduce a load using our wind and ponding. So we added the ponding load results into the distribution of load chapter that you can have a quick look into the results. So let's step into my first example. It's of course an imaginary example. So I did not pay a lot of attention to define the correct member hinges or the correct stiffnesses of this construct. It's a small tent, 3 times 3 meters, and it was standing in my garden. So I did purchase something like this on a normal online seller. And due to the fact that it's better to sit under it if it's raining, I let it stand in my garden. And unluckily this year there was a bigger storm and bigger rain amount. And once I came back from my weekend vacation traveling, I had to see that my tent was destroyed because there was a big water accumulation in my membrane due to the fact that it was raining and windy very lot. So it did accumulate. One bar did bend horizontal because there was just a weak stiffness. And well, I'm currently trying to fix it maybe next year that I can use it again. So let me introduce you into my example. So as told, it's just a small tent with aluminum profiles. Then we have a normal membrane put on the roof as triangles, so 4 times triangles, and I did sum them up as a surface set. So you just have to mark them and you can combine a surface set because this allows you to load it quite easy if you want to. And if I make it a bit visible, you can see that there's an inner cross in the plane and some column on over here where the membranes will then lay in. And I tried to couple my membranes, as you can maybe see, with some rigid members, where I gave them some nonlinearity because of the fact that, of course, if some elements are not connected with our FE mesh, then there's no check if the membrane will deform quite a lot below the member, that they will touch and distribute forces into each other. That's usually linked to hydrocords or independent meshes. So I will try to at least model it in the small part that the membrane can lay down on the member so that the behavior of the membrane is most likely like I would expect in reality. Line releases are not allowed for such a type, so you may use such couplings. They were also introduced in RFM5 already, and they may work. I'm just putting a normal pre-stress on my membrane. So I use the projection method because I expect or I want to reach such a tent shape where I enter some imaginary values. They may be not practical values, but the pre-stress will not be that high because usually you will have also some cables tensioning this small tent. And then I will load my tent once with such an imaginary wind load, so a high load on one side, a quarter on the other side, and also a high load on this side and just a half normal pressure on my surface on this side. So just to the system, and then we now come, of course, to the feature load. So it's a normal surface set or a normal surface load from the load type ponding. So if you are searching for the load, just create some membrane structure or some normal structure, check out for a surface load, and then you will find the ponding load. The ponding load allows you to define a specific weight of, let's call it material, or as you can see in the sketch, rain falling on your structure. And you can choose that it will be filled fully if you do not define an amount of precipitation, or you can define an amount of precipitation. So then the iterative calculation will stop once the amount was rained on the area. It is necessary yet to do a calculation of theory third order. So my first load case 3, will be 1 millimeter per square meter, then the double amount, 2 millimeters. And then I would, of course, like to check what will happen if it is raining very much. So this will be then some state of equilibrium when the water will fully fill my membrane, and then there is some equilibrium found and the water will flow down because the surface is fully filled with water, and there will be some low point and the water can drop down. Okay, so I did sum up everything in load combinations. Maybe you are already used to our add-on, but it is now not the case that you have only one initial state, like in RFEM5, where you were able to define some form-finding shapes by defining loads and pre-stresses. You are now fully free in one RFEM file to check what different form-finding states may bring you in your structure. So for my example, in the first case, I want to pre-stress my membrane. Also, as you can see in the load case with the activated dead load material, and I did deactivate my rigid members because the shape should be found, and I expect that the membrane will not lay down on the members without these links, and later I will use these links. So I use my initial state, and I assign the pre-stress, of course, and the wind load, number 1. This is CO1, and in CO5, I use the other wind load. So CO1 and CO5 are my initial form-finding states, and then I load the states with the 1 millimeter, 2 millimeter, and full load. So the same for the other stuff, and I then considered my load combination as initial state. So if I now calculate our design situation 1, which is most likely the new type of envelope, which sums up all our load combinations. So you do not need to define an envelope by your own. It will start, of course, with our first initial state. Then it will load CO1 and 5 with our wind load additionally. And then it goes into the multi-core calculation because now the stiffness matrices are the same, and it will check up all the other combinations. So first, we want to check our wind load like this and the amount of rain like 1 millimeter. I will hide the forces. Then you can, of course, always think about which type of topology you want like your structure to be shown. So I would like to have the deformed state. And of course, I would like to start with the initial state. Where we do not have yet some raining. So I would just check for the contour lines. So it's the pre-stress I put in my structure. And then there is the, let's call it heavy vertical load. And as you can see, my membrane will, due to the effect that the load is higher than my pre-stress, bend down my membrane. And the highest point of my members are 2.50 meters. And my membrane will be like 8 centimeters below this point. So this is most likely the lowest point, and this is an available point for water to accumulate. So if now the rain comes on my structure, nothing really changes. But if you now check for our water depth or water level, you can see that there is some water accumulating. Let's check from minus y. So it's not fully filled because 1 millimeter will not fully fill the square meter we have. And you can as well, of course, inspect the forces. as shortly shown, you can also check the distribution of loads and then check also the bonding loads distributed on this area. So my water now flows into my surface set, and if I increase the precipitation, so switch to the next combination, you can see that it will accumulate even more. And last but not least, it will even fully fill my hole, and I will then receive a final result. It will not influence the membrane with its stiffness and the pre-stress more, because it will afterwards just drop down at the edge, as you can see in over here, where the member is a 1D element, so it will not take into account the height of the member. That's not possible in a 1D, but it will now flow down, and this is then the state of equilibrium. So the same would go if I load a higher wind load on the left, so you can see it accumulates on one area and then on the next area. And last but not least, it will accumulate even more in two parts of my structure. So this way I could maybe check if the rain will affect my construction, and if it's weak enough, we can see that the members will bend like this, and well, my tent it got destroyed because it was just weak in this direction, and now I need to fix it. I do have a second, let's call it simpler file. So let's open the second file. It's as well, once again, a more imaginary structure. It's just a membrane which gets pre-stressed with its dead load in a horizontal way. So due to the minimum dead load, there will be some starting shape, what you can check with the contour lines. So this is a 3-meter member height, and we have like 2 centimeters of deflection already into the Z direction. So if it now rains, I've chosen a 1 × 10 millimeters, 50 and a bit more, so the full way. You can now see it a bit better because it's a quite easy structure to observe how the rain will then fill your construction. So if we check for 10 millimeters and the water depth, you can see that this area is influenced. And if we check for the water level, you can see that with regards, of course, to the initial state, the membrane will, of course, bend more because, of course, we now have the pre-stress brought into the system and additional loads, and it will be filled. If we have a higher ponding, it will be filled even more. And if we have a maximum ponding, there is an equilibrium where then at one side, because it's an autotropic membrane, we will reach the lowest point where the rain will then just drop down and fall down. Okay, so this for the ponding feature. I step to the next feature, which is yet only available in the pre-release mode. So it's for our internal testing, but pre-release means that it's gonna be published soon in a Grandmaster. You can then check for, of course, in the extranet. It's the surface load sec from the load or calculation method projection. Maybe you have taken care, or you have taken place at my latest webinar where we have checked cushions. There we did show the surface load sec for the standard method, and now we filled the gap and also are going to introduce the surface load sec for the projection method. So the definition is sec, so you do only have to define a ratio of your inner forces and a sec of a bending height. And then the iterative method will, of course, find then the concerning equivalent pre-stress loads for the surface. It offers orthogonal or radial distribution. And this, because projection is usually, as you have seen in my latest example, meant for a tent structure, this is now meant for simplistic shapes. Okay, let's jump into the pre-release. Remember, these files will not be able to be opened with the load type in your normal customer version because it's not yet released. So we have 2 quite easy membrane structures because we only want to discover the acting of the membrane, and we do not care about some stiffnesses of the construction under it. On the left side, we have the normal standard calculation method sec definition. So maybe to reintroduce you, it's once again a load type as a depending load. Now the form finding is a load type not inside of a surface, but it is now an RFM6 surface load. And there I've chosen the standard method with a ratio of 1 and 1 into both directions of the membrane. And I have a quite big seg because I want to show you some graphical deformation of 2 meters. It's maybe a bit high. And on the bottom for the circle, I have the same definitions. On the middle, you can see now the projection with the same input for the orthogonal load distribution, and on the right side for the radial load distribution. If we now run this pre-stress load case, it will now, of course, do a large deformation analysis. It will then iterate until we reach our certain point of convergence. So if you hit this button, you can go into the static analysis settings and you find the tab form finding, where you then will find the information on how many iterations you want to load this pre-stress, depending, of course, on the structure and what you want to reach. And you can as well effect the precision or the tolerances if you want to for your calculation. So if I do not show the results and will only have a look at the mesh from the top, remember the left is the standard and the right is the projection method. This is I think the most easiest point to evaluate what both calculations will do to the membrane. You can see that in the standard seg, we will have a fine mesh in the middle. So from the deformation of the mesh elements cursed by the calculation. And for the projection load, we have a quite stable net. So it does something with our calculation. If we check up for the shape, so it's the contour lines of the membranes, you can see that they are most likely similar. We quite reached our goal of 2 meters. We now have 2 meters and 3 centimeters. So we may still change the convergence in order to reach 2 meters if we want to, but this result is now feasible for me. We can see on the left and on the right, that's most likely similar shape, or, well, you can see that we have some bigger circle on the standard method. But now the most likely easiest way to check up is to have a look onto the internal forces of the surface. So let's check for an X and an Y. So this is the ratio the program will find for our pre-stress we will put inside. And even if you now check the principal internal forces, so these alpha M, this is giving you some, how it's called, trajectories on how the forces will be applied to the structure. You can see that this is a bit smoother distribution of the surface load. So this is most likely up to you, of course, what method you prefer in order to get your shape and the pre-stress into the structure. So let's go on with the last feature for today. It's also yet in the pre-release mode. It's a new material model we are going to introduce to you. It's the orthotropic fabric nonlinear elastic surface material model. So it's available for materials of the type fabric. Due to the fact that it's nonlinear, I think it's going to require a nonlinear add-on then later on, of course. And it offers you the orthotropic nonlinear elastic behavior of your membrane material. And this is meant mainly yet for 2 weave patterns. So if your membrane is having a plane weave, which is symbolized like this, due to the production, this model is going to represent it with some element in the background, or if it's a basket weave like this, there's also then some representing element model in the background. Some more information to this material model. This is a microstructure based material model, and as told, we will now, or for this in the background, there is a representative volume element, as you can see in a sketch in over here. And this is most likely modeled with inclined gables for the fibers due to the production like it is woven. And we have some vertical truss between those fibers. And if you also want to apply a 2D foil element as a coating, you will have the option to enter a shear modulus, like you can maybe see in the sketch. The sketches will be improved, of course, but it should be possible to introduce you into the model system. So all you need to enter is most likely, of course, as always, if you have some material properties for the orthotropic material, you will need to enter them. And then you only need to enter a ratio of the height to the length of the volume element. So you can see the height is the stitch between both fibers, and the length is then one element most likely. So it's one part of the weave. Okay, let's step into the program and get you to see some colored model shapes, of course. So first I want to show you this file. It's made by our developers. So it is meant like this. On the left side is the RVE, so the representative volume element, as I told, cables, truss, and a coating if necessary. So meant for different FE mesh sizes and also meant for the weave pattern we have. And now you would go into your membrane, which is more easier, of course, to define than defining such an element. You will go into the material definition, go into our library, choose some fabric material type, and then you will be, once it is released, please remember this, able to define an orthotropic fabric nonlinear elastic material model. If you don't care, you can just uncheck the user-defined material, and then the preset is taken like this in the background, so a coating and also some ratio of the height, or you are known to your material, which should usually be the case, having a membrane material. Then you will check the user-defined material, and you will be able to manipulate, of course, the E-modulus. You can define a coating if you want to, and you can define a ratio of this. So this one is an example to test if we have now support movement, what results can be achieved with the nonlinear material model compared to the element which is in the background. It will not fully match, depending, of course, on the type of convergence where you then will set your equilibrium. But you can maybe see in the support forces we are close to the reasonable results. And what we would maybe expect by simulating such a weave pattern with such a member material model, or with now our upcoming nonlinear material model. So let's show you maybe this on a simple membrane structure. I think the structure is already known if you already attended a webinar of us. It looks like a paper plane for me, which is supported by cables on the edge and nodal supports. And then there is a prestress we are giving on, just a normal symmetric prestress into local X and Y direction with the standard method, so nothing special. And we want then to load it with a vertical load, because doing the prestress, so the form finding for the structure, we most likely define the shape we want to reach with our inner forces. So the material properties will not pay a big amount. And we will receive then a shape, a contour shape, which is similar, even if we use different material models. That's maybe the point I have, of course, to tell you. So the left one is using the normal linear elastic material model for the membranes. And then I have defined 3 different types. So the next one is using nonlinear elastic, where I have defined the shear modulus being the same like for my linear one. So if I check it, it's the same shear modulus. And then I have defined one material model where I got rid most likely of the coating. You can as well enter 0 in here. And the last one will have an increased shear modulus, so a coating which is bigger or having a bigger influence into your fiber structure. But still, as told, we receive the same results for our form finding process because the boundary conditions are the same. And due to the fact that we define the prestress, we will receive now in this state the same shape. If we now apply a load to our form point structure, all the material properties and also the boundary conditions, etc. So even if you now would have members, the stiffness of the system will now be given a bit more intention than it is in the form finding process. Also, the pre-stress will maybe redistribute if you use some form finding supports. I will show you soon how they are used. We will now see different results. So we can directly see it. Maybe if we move it like this, so let's do it with the cube. If we check our view from this angle, we can see that this is our linear one, and then we are going to be nonlinear, and the deformation will already differ. Well, since we have a quite high membrane, this is not the easiest way to elaborate. So let's check for the inner forces of our membrane. We can see now that the definition of the material will have a certain outcome, of course, for the inner surface forces, or as well for our boundary conditions. Okay, so I will just close this one, and I will now come to my second part of my presentation. I would like to show you some certain examples, what I was thinking of. And I will start first with an easy cable. So I'm going to the Blue Ball Center, and as you can see, maybe if you already used the project manager on FM5, you can quite easily also filter your projects like this, which are on the normal local storage. You can as well enter your account. Maybe I quickly show this and also check in, well, it's now the German interface because my account is a German account. Go into the development, and this is the place where you can find features and also bugs if they are corrected. I will now load my next file. This is called cable, where I would like to introduce you once to our cable loads. So I will just run it once, the file. It's the same cable. It's a 10 times with a 45-degree angle cable. So 10 meter times 10 meters. So it's 14.1 meter. And then if we go into our load definition, as told for the surface loads, it's not now a setting of a surface or a setting of the member. It is a load you can assign as a member load. The load type then needs to be chosen as form finding, and then you will be offered to two definition types. So you are able to define a geometric force or load, where you can see what is then going to be put into the calculation in order to reach your pre-stress or your normal force of the cable. And today I would like to show you our force loads, where I will maybe try at this example to get you known to the differences. So the average force in members is, I think, quite easy. So the form finding calculation tries to find an equilibrium for the cable with the deformation that 5 kilonewton will be reached. So we now have such a bit of bending, and well, it's of course depending on how high you set the precision in the static analysis settings. We will have 5 kilonewton in here. They're a bit lower and they're a bit higher. But all in all, if you sum it up, it should be the average of 5 kilonewton. Maybe I will close the table and show a second window underneath where you can directly also inspect the deformation. So the deformation, of course, will change depending on which load type we will introduce into our cable. So this is the left one. So the normal force, we will have such a deformation. We can as well only check for the bending into the global z-axis in order to investigate, but I think the vector is a bit better in here. The next load is the maximum force in the member, or even the minimum force in the member, which is gonna or trying to be reached. I kept the 5 kilonewton, and in the upper one, you can maybe see that we will reach 5 at the top because it's the maximum we would like to allow for the cable, and we have a lower part at the bottom. The down one is that we would like to allow the program to find a pre-stress with minimum 5 kilonewton. So it's going to have 5 at the bottom, where also the lowest point is on over here in this file, and have a bit more in the high point. So depending on what purpose you would like to introduce, this is a type which is achieving these results and having an influence, of course, to the results. So we have overall a higher normal force on the lower one, so the deformation should as well be a bit less. The next one is able to define a horizontal tension component, which is then, of course, redistributed to the local force of the normal force. Due to the fact that we have 45 degrees, we expect something around 7. So it's, as you can see, it's reaching something about 7. The pre-stress is higher than 5. So let's just check quickly for the deformation. We have a lower deformation as in the other file. It's like maybe the way you will introduce the pretension into your cable. You don't have to think about what normal force can be reached in the cable. You can just simply add the X component and let the program do the rest for you. The next load is the tension at the Y end. So Y is having a look on the cable, the start, and J is the end. You can also hover over your member and you can see a small arrow. So my members or cables are going, it's hard to catch if I'm having the window a bit smaller, are going from bottom to top. So this is the start and this is the end. So I'm now trying to define 5 kilonewton at my start in the top picture and 5 at the end in the right. So it's most likely, if you remember, we can see 5 at the top and soon or close 5 at the bottom. It's the vice versa of this load, most likely in our example, which is also shown in the deformation. It's most likely vice versa, and we will get the normal force in the member. We will now quickly skip the minimum because I will show you this one on the next model. Due to the convergence reasons, if we model everything in one file, it may influence the convergence of our form finding for separate part systems. The last one in this model is the force density. For this, you can see that there's some load with a yellow arrow pointed out. And if I check into my edit formula, I can see that I have typed there something like 5,000 divided by ml, which is giving me this result. So it means that by the formulas, they are meant to be in SE units. So if I want to introduce 5 kilonewtons, I would have to enter 5,000 newtons, and I divide it by ml. ml is a parameter I have set. So if you click into the global parameters tab, maybe also already known to you, I now use here a formula in order to determine the length, so the unstressed length of my member without doing anything to it, which is 14.14 meters. Well, of course, you can calculate it by your own, but maybe you change the length, then it will do the stuff for you and you don't have to think about it. And this will leads the force density to be like this, so 0.35 kilonewton per meter. And this should be somewhere close to my 5 kilonewton I give there in the average inside. And well, you can see the deformation behaves a bit other to the left file, but this depends then, of course, on what you want like to achieve. So let's close this file and go into the other cable file where I want to show you the minimum force gathering for your cable. So on the left side, I have defined a form. You can get rid of this load magnitude. We will improve this in a future version because the minimum tension is doing like an optimization. So it's really looking for the minimum tension at the start. So there's no starting value you need to enter in over here. And the minimum tension at the end is looking for a minimum tension at the end for this cable having its inclination. So it's not 45 degrees, it's now 22.5 degrees. And if you run the calculation, you will get, of course, then an inner force distribution for your cable, which is like this. So it is similar for both, because I'm looking for the minimum force at the start on this file and here for the end at this file. And this is most likely like, switch off the grid, like going or searching with the functions of the force definition for tension at the Y end. So we will most likely iterate internally. So this is a stable construction. We can have it less this is also stable, this is also stable. And if I would lower it even more, then my structure will become numerically unstable or nonsense. Inner forces will arrive. And then this is what this function is doing internally. So it's a minimum force definition to reach a certain convergence or equilibrium. So of course, the dead load is activated for both models. Okay, so I did not model a lot yet. So let's go now to 3 models where I would at least show you how you can model something quite quickly at one example file. So I will open now, I have to search it for the name, of course, my next file. The structure is already known to you, so it's our paper plane. Let's call it like this, with this time a column at the edge and some cables. And I want now to start to model this structure and show you how quickly you can do it. So of course, if you want to start with the form finding, please enable the form finding add-ons or the form finding add-on. And well, then you can, of course, also define material sections and so on. So I will not show it this time. So I would now start to define a normal rectangular plane as membrane with membrane material, which is then having a thickness of 1 millimeter. So I simply draw a 10 times 10 meter rectangle. I would just cut it by half in order to draw a line, and then I will divide the surface by intersecting lines. Due to the fact that it's usually better to define a grid for your surface, I double click on both surfaces, assign specific axis, and I rotate one axis parallel to a line. So I would like to have my local y-axis of the surface pointing in the direction of this bottom line. Okay. I now want my edges of the membranes, because they cannot be free edges. Otherwise, the membrane will, if you pre-stress it, that be quite weak in this direction. We always need an edge member, which will be a cable in our case. And I would just use a defined cable where you can, of course, quickly check the material properties of the cable. So I assign it at the edges. And then, well, it's a flat membrane. So I can just mark both nodes, double click on them and move them 5 meters into the height. All other connected elements will, of course, then be manipulated, making it quite easy for you. And then I will draw some columns. They will be, in my case, truss limited to only n members. So if you are curious and you do not know what all these member types are about, just hit F1 on the keyboard. Then usually the browser will open and it will directly guide you into the member online manual. You can hit truss only n and you see that the truss type is only with a stiffness E times A, and it's only able to absorb normal forces. So you don't have to know everything. You can just quickly go into the manual. For this, we will use our aluminum profile just from my tent I showed at the start. So we will now just draw this column in over there, and we will copy paste it by keeping the control key on the keyboard and copy paste it to this node. We will now define, or we can now define as well some of our cables. So you can hit the new member button, and maybe you do not even know yet about, but you can also select object properties in the graphics. So if we now do not want to have our column, but we want to have the cable definition we already set for this cable, we just click the cable and everything is then assigned to this member. So I want to draw it 5 meters abroad from there to there. And then I want to support in over here everything with such a nodal support. And then I just go over, mark my both cables, and I will rotate them as being a copy in 180 degrees. I will choose a point. Luckily, I have a middle point, of course, on over there, and I hit OK, and then it's rotated. I just quickly add also support on over here. Last but not least, I would like to consider also form finding supports. So for this concern, I would just simply add some XY supports without any non-linearity type on over there. because, as you maybe already know, it's not a non-linearity type anymore to add some form finding supports, but I will show you how you can then define them. Last but not least, we are going to just simply insert a form finding pre-stress of 1 kilonewton as a standard load definition for our construction. So if we now would like to check how the construction will behave, if the supports will act or not in this case, the keyword is now to go into a load case. You can see it's already created because I did not delete everything. You can now define a structure modification. So we would go into a new structure modification, and there I would be able now to deactivate objects. And I am now able to deactivate supports, for example, on nodes. Keep in mind, it's meant to be on nodes. So I will now create a new object selection where I can define that I want to have in this object selection nodes with the definition node number, and this should be equal to these both nodes, so 1 and 3. Okay. And I now consider this structure modification. So for the program, this is like the last concept of AFM5. These supports will not act in this case. So they are not form finding supports, so they are not there. But you can use such a structure modification, of course, later on by combining then a combination and in order to disable then the supports. For the other pre-stress, which will then be similar, let me quickly delete this because I will, of course, copy my load case. I already find a different structure modification where I will deactivate members, and my deactivated members should be my cables. Okay, so if we now calculate all, of course, yes, the load combination 2, we can get rid of them. Let's calculate all once again. We should now find two shapes. Ones where the nodal supports are deactivated in our load case 1, and in the second, our cables are deactivated. Maybe if you're used to something like this, of course, it does not make a big sense to deactivate cables because the nodal support is having quite higher stiffness. But well, to be correct, we can, of course, then check it without the cables. So depending on how fine you would like to achieve results, program is going to calculate. Maybe I did something wrong this time because it's not working as expected. Of course, well, I have to set some nodal supports, of course, at this edge. Otherwise, it's the deformation will look quite interesting if I do not set nodal supports at these edges. Yeah, this is what I would like to achieve. So we can now once again check the contour line, and we can of course see that in our second file where we deactivated the members, the full force should go into this side. And did it converge? We have to calculate, of course, now load case 1, where we then deactivate the nodal supports, and all this the force should go directly into the cables. We would see a similar shape, but now then you can see that the force is going into the cables. So it's depending on what you would like to achieve and how your form finding structure is going to be built. You can use these tools in order to, of course, inspect your shape. So let's jump into the next example. You can, of course, leave the toolbar center open and not close it, depending on how much files you have. So this is a cable net I would like to show you now. It's not that hard to introduce, so having a look on it. It's a cable net 10 times 10 meters once again, and then I have some cables going through it, split by 10 times in this direction and 5 times in this direction, and then I applied an angle of 20.25 degrees. What I would like to show you at this file is that you can see my cables are split So it's quite hard sometimes to apply now a useful form finding load on them. But maybe you already heard about, well, member sets you should know from RFM5, but you can also use them for our form finding structure, like surface sets and solid sets, because they are now not only used to design a split member as one member in add-ons. No, you can now as well define so-called member set loads. So they contain most likely all the definition types what a member load is able to do. So you can now define member set loads. In order to do this for our file, you could of course now single choose these members or these cables, hold the control key, and do the stupid or annoying thing to mark everything after each other. Or you now go into our visibility tab, so the view tab, and you can define object selections. So it's like the last thing we used for structure modifications. You can now easily, according to the older option in RFM5, edit select special. This was most likely moved into this tab where it makes more sense, I think, where you can now choose that we would like to select every member, what is parallel to a member. And now we want to have all members which are parallel to this member. If we check the statistics tab, you can already see the yellow highlighted members will be chosen. If we hit OK, and we now only display this visibility, you can see that we now get a quicker influence into our members and object selection, and we can mark everything, right-click on them, choose members, and create member sets. You can see that the program is that intelligent that it will not combine these split members, but it will combine such a row to one member set. So the same can also be done, of course, for other members. So let's do a new one where we want like to have the members parallel to the other members. You can, of course, then cancel the visibility and choose this one. And then we can see in the statistics that only these members will be caught. So by doing this, we are able to define member set loads. And I have now defined them this way, that I have a geometric member set load for 101% of relative member length for my rectangle. And in the inner member forces, I have chosen 2 kilonewton into this direction, and into the Y direction, I have chosen 1. So remember, if you want to compare different pre-stresses in one file, you just simply have to copy this load case, for example. Then you can activate the table, or also just mark multiple forces in over here in order to go in and quickly change it from 2 to 5. That's most likely all what has to be done. You can now hit calculate, and then you can control, once again, the load combination is empty. That's funny today. Okay. You can calculate then your bow form finding shapes. So the load combinations do not like me today. So you can see we now have with the 5 kilonewton meter in this direction such a shape where we can quickly investigate the normal force distribution. So we most likely reach 5 kilonewton in this direction and 1 in this, and all the others are by the geometric boundary identified. So if we would like now to observe the deformation, we can check it like this, and best thing is to scale it for 1. And if we have a lower pre-stress, like 2 kilonewton into this direction, by pressing F5 on the keyboard, we can quickly run the calculation of the load case. We'll have a different or a bit different deformation, but the bigger difference can be found in the inner forces. So last but not least, I would like to show you a last example. It's the modeling of a top ring of a tent. So I tried to investigate in such a tent structure. So quite easy, just a 5 centimeter circle, and at the top 1 meter with an inner column. What the influence of a ring may be. So I think most likely often it is modeled like this, that you will have such a rigid cross and also a rigid circle at the top of your tent. The next option I can imagine is having a stiff surface at the top. And a third one I can imagine is having like normal members at the top with their stiffness. And if we now apply equivalent projection pre-stress on our structures, go on and find the calculation. Sometimes you need temporary supports depending on the numerical stability of your file. For this, we don't need them. We can see that the deformation should be similar and also the inner forces. So the deformation should be similar to also the inner forces. But then the member forces can, of course, differ from our rigid connection and over here. So we have here rigid members where you can, of course, display also the results on couplings. Well, the surface will not give us any clue about the forces. We are able to evaluate surface forces for this. Or we now check the member ring where it will also be influenced most likely by the stiffness of the member. So depending, you can see that it will deform like this, maybe a bit, of course, exaggerated. It's only 6 millimeters, but it's not that stiff like the other constructions will be. And well, it has a small influence most likely into the inner surface distribution. So there's no big pro you can achieve by doing one or another model. I think it's up to you on what to choose for such a model. Okay, so let's close ARFEM and step back to the presentation. I am already done, so I have a last slide for you. So the prospect for today, we are of course working on finalizing the features of the pre-release version. So the two ones I have shown you. We are hardly working. We know it's quite required by you to export also the form-found structure as DXF formats. Well, there were some troubles to that part, but we are working on it. And the last one is also, of course, the development of our cutting patterns add-on in order to have a full package of membrane construction and also the possibility, of course, to export cutting patterns to hand it over to your cutter. All right, so I'm done, Andreas. I would like to hand back to you. Thank you for your thanks for attending.
Okay, thank you for your presentation. Before I show the website where you can find the recording next days and also the model files and so on, I would like to give you a small hint. If you want to get a free product demonstration, for example, or you would like to get a non-binding offer, just contact our sales team with that link in the PowerPoint slide, or you can scan the QR code. Yeah, just contact them if you have questions or if you want to book your free online appointment. Okay, then I turn back to the website. Just a moment. Okay, that's our website, lubal.com. And under, oh, that's the German website, sorry. I switched to the English website. Under news and events, you can find the webinars. That's today's webinar, and that's the planned or scheduled webinars. And you can also find our previous webinars. We record all our webinars. I click on today's webinar. You will get an email in the next days, with the link to that leads directly to that page, and then you will find the recording here in the middle, and you can already download the presentation slides and the models. Just wait for our email, then you will get also an attendee certificate. Okay, that's also all from my side. I thank you for your attention. Thanks to Stefan for the nice presentation. Thanks to Andreas Niemeyer for answering the questions. I wish all a nice rest of the day. Maybe we meet each other in a future webinar. Bye-bye.